Hello and welcome friend in this new video where we discuss about Riemann integration. It is an important part in the real analysis, and up to we know that it was limited to the region, area and geometrical parts integration, but Riemann has uh, developed it as a summation point of view, and therefore it is in the honor of Riemann, it is called as a Riemann integration. Friend, and close interval a comma b. Suppose this is a close interval a comma b. On the real line, this if a is here, b is here, then we can take a point in this region as x1, x2, x3 dash dash dash. Then we see that this point divide the region of close interval a to b. To be definite, it gives us a partition of the closed interval a comma b, and this partition is the set of points. Suppose P is a set of points x0, x1, xn, and it is like that x0 equal to a, x0 is less than equal to x1, x1 is less than equal to x2 dash dash dash, xn equal to b. Then such a set of points is called as a partition of a closed interval a comma b. Then the difference between these x1 minus x0, x2 minus x1 dash dash is called as a length of this partition, length of the interval, or in the these are the sub intervals x0 to x1, x1 to x2. These are the sub interval of the closed interval a comma b. Now friends, suppose consider the interval xi minus 1 comma xi, then the length of this interval is xi minus 1, and we denote this by delta xi. This is the symbol which we are using to denote the length of the interval xi minus 1. For example, delta x1 equal to x1 minus x0, delta x2 equal to x2 minus x0. Now if f is a real valued function, on closed interval a comma b, as this is a function defined on a closed interval, it is a bounded function. If it is a bounded function, it has a bounds, upper bounds and lower bounds. All the values of, suppose capital M is an upper bound and small m is an lower bound, all the values of the function lies between capital M and small m. The function is bounded on the whole interval a comma b, therefore it is bounded on the subintervals x0 to x1, x1 to x1 to x2 like this. Suppose capital Mi and small mi are the supremum and infimum of this function in the interval delta xi. That means in the interval delta x1 supremum is capital M1, infimum is small m1, delta x2 supremum is capital M2, infimum is small m2. Then we form a sum capital M1 into delta x1, that is supremum in the interval delta x1 and length of the delta interval delta x1 plus capital M2 into delta x2 plus capital Mn into delta xn. In short, we write it as summation of capital Mi into delta xi, I varies from 1 to n, and we call it as a upper sum over the partition f. This is we are talking about a particular partition P having the points x0, x1, x2, xn. Now friend, you can see that if we take a particular example, suppose we take a particular closed interval 1 to 10, then one can take that 2, 3, 4, 5, and for example 1, 2, 3, 4, 5 and 10. This is my partition. So this is one of the partition. Someone takes 1.1, 1.2, 1.1, 1.6. This is another partition. So there may be more than one partition of the closed interval. Here we have taken a particular partition P, and in that partition we have capital Mi and small mi are the supremum and infimum. Therefore upper sum over the partition P of the function f is denoted by up of equal to summation of capital Mi into delta xi. Similarly, we can take a sum of lower sum small mi into delta x small mi into delta xi summation I is equal to 1 to n, and we call it as a lower sum. Okay, what is this? Small m1 into delta x1 plus small m2 into delta x2 plus small mn into delta xn. So this is the lower sum over the partition P. But we know that just I have told you there are how many partitions. We can take number of infinite partitions, and likewise if we take partition P2, P3, P4, we have one upper sum and one lower sum, and we get a sum we get a set of upper sum and lower sum. So denote that set of upper sum by U. And what is a U? U is the set of upper sum over the partition P. P is a partition of closed interval a comma b. Then take the infimum of this set, and the infimum of this set is called as an upper integral. It is called as a upper integral. Similarly, we have a sum of lower sum, a set of lower sum where P is a partition. Then take the supremum of this, we denote it by capital L, and take the supremum, and we denote this value by lower, we call it as a lower integral, and we denote it by the symbol integration a to b, where bar is taken over at the lower limit a. Then for each partition, then for each closed interval or each function we have an upper sum, and for each partition we have an upper sum and lower sum. Then we have a set of upper sum. From the set of upper sum we are taking infimum, and that infimum is called as a upper integral. Again we have a set of lower sum, we are taking the supremum of lower sum, that supremum is called as a lower integral. Okay friends, then we know that the function is a bounded, therefore the upper sum and lower sum, the supremum and infimum are likewise capital Mi is less than equal to capital M. These are the bigger, this is bigger value and this is a smaller value. So here you can see that if we take small m into delta xi less than equal to capital small mi into delta xi less than equal to summation of capital Mi into delta xi less than equal to capital M into delta xi, and taking a summation. Taking summation, capital small m is independent over this I is equal to 1 to n, is not dependent on I. So delta xi, let us take summation of delta xi, I is equal to 1 to n. This is equal to delta x1 plus delta x2 plus delta xn. What is delta x1? This is x1 minus x0 plus x2 minus x1 plus xn minus xn minus 1. Here you can see that x1 get cancel, x2 get cancel, and we remain with xn minus x0. This is nothing but b minus a. And therefore this sum becomes m into summation of delta xi. This is not nothing but an lower sum. This is nothing but an upper sum less than equal to capital M into b minus a. And friend, here you can see that the function upper sum and lower sum, this is an important inequality. Remember this, we require this for further calculations. Now we have seen that infimum of the upper sum is called as an upper integral. This is the symbol of upper integral. Supremum of the lower sum is called as a lower integral. We have this symbol for lower integral. Now whenever these two values are equal, whenever upper integral is equal to lower integral, whenever upper integral is equal to lower integral, then it is called as a integrable integration of a function between the limit a to b. And this condition upper integral equal to lower integral is called as a Darboux condition, So this condition gives us, this is called as a Darboux condition. And we have a definition of the integrable function. What is the integrable? When we said a function is an integrable, when upper integral equal to lower integral, then the function is called as an integrable function. So friend, thank you for watching the video. I hope you have get the definition of the function. Okay, so remember that when the upper integral equal to lower integral, the condition is satisfied, the function is called as a Riemann integrable function. Riemann integrable, it is called as a Riemann integrable. Okay, so what is definition of Riemann integrable? When upper integral, we denote this upper integral like this also, equal to lower integral, then the function is called as a upper integral function is called as a integrable, Riemann integrable function, or we can simply say that a function is integrable function. I hope you have got the definition of Riemann integration.